multiply by 2. It goes twice that distance.
Right, it's because it's just the first term.
More sense.
Makes sense.
I don't know how to do it, but I know what
No. You know what it is? Because it says total
I
vertical distance. You have to multiply it by 2 because you have to
That's
count
what I
all
did.
the way up.
Did you get a
That's
haircut?
what.
That's not
what
I've been saying.
And then you subtract 6.
That
gives you 42.
well, you don't need to subtract 6.
You do because it never goes up.
Oh my gosh.
It only drops.
Yeah, but if you set it at n equals 0, then it cancels out the 3 halves and it just stays at 6. And so the next one would just be.
It'd be 6.
Yeah,
And
what are you gonna cancel?
Oh no,
Well, if you set it at n equals 0,
Thank
you go to the
That's
even.
what I like to
You
do.
just started at n equals 1.
Think about it, you put in n equals 0, it just goes 6, and you add the next one, and then you get into like the 3 halves sequence.
Did you still get 42?
No, I got 12 that time.
So if n equals 1, then our initials will be 6 plus 2 times 1.5 over.
Yeah, wait a minute. That's good.
No, this is right. 6 plus.
I drew you a picture of what I think it would look like if it had some horizontal velocity too.
It's frozen.
Oh, do you see it's not a great picture or what?
I really like all the colors.
Yeah, there we go. No colors, just one. So I don't know, like, does that make sense as far as what
No, it's 42.
it would look like?
Okay, well, I understand.
I really like the idea of a picture.
I drew a picture. And then undrew it. Yeah.
Yeah, pictures are helpful.
And they went back and traced it again in the
Traced it back.
All right, well, let's see. Let's see if this makes sense. If I was just going to be very, like, elementary schoolish about this, or maybe middle schoolish about this, couldn't we say that the total vertical distance traveled would be something like this? 6 plus 3/4 of 6 plus 3/4 of 6 plus, wouldn't that kind of thinking get me from here to there to there to there?
Wasn't that not the total vertical distance?
Well, I'm not done. I'm not done yet. I'm not even close to being done. I've gone just the yellow part only.
Okay, I got you.
So like I've gotten to that point, and maybe I figure it out at this point. Maybe I don't. Maybe I keep going. Maybe the projector will turn back on. Oh, someone's stealing my screen?
Algebra 2, let's learn. Spina, I love, Spina.
No, Mrs. Skeen.
Skeen?
Yep. She teaches in here sometimes. Yep. Of course. Hijacker. Pirate.
5, do we get our revenge?
She's a
Oh yeah, we could.
Yeah, they would be so
Screen
confused
pirate.
if this popped up on their screen.
We'll do that in a minute. How about, see if we can do it. Sometimes it won't let me. I don't understand why I can be pirated but or hijacked.
You see
But
that pull up a Word document that says stop stealing our screen and then just broadcast it to the
there we
side.
go. I'll try. We'll try that at the end.
I didn't know it was going to
Okay. So guys, if I wanted to keep going, wouldn't I need like that next bounce? Wouldn't that be 3/4 squared times x plus 3/4 squared times x?
Yes.
That would get me all the way through the yellow bounces plus the light blue bounces. So maybe at this point you would see a pattern. And can you see how this is sort of a lone wolf, the 6? I feel like if we really wanted to, we could kind of force that 6 into the summation. But I'm sort of thinking, why not just do 6 plus a sigma? Right? We could force that 6 in there, and we could think, where do I need to start my n to get this to be where I want it to be? To me, this feels easier. Just say 6 plus a whole bunch of things added up. That make sense?
Yeah.
I don't know. And then I would say what's happening inside. Well, isn't everything inside the sigma going to be 6 times 3/4 to the something? I haven't filled out my little n equals yet, but I will. So if I start here and I take this one out, where would my n need to start? 1. That's me doing it. If you started your n back at 0, things could look a little bit different. I'm okay with that. It just needs to be logical and go together and make sense.
If you included the 6 in the summation, would you start at n equals 0?
You could, but then you'd have to subtract something off the back end, right? Potentially, if you set it up in the same way. But then I also have to notice one other thing here, right? If I only did that part right there, isn't that just like the front side of the bounce each time? It's like it would just be there and there only, but there's 2 of those, right? There's 2 of them there, and there's 2 of them there. So I need to also multiply this whole inside by 2, right? Because each time it's going to be a 6 times 3/4 to the something plus 6 times 3/4 to the same thing, dot, dot, dot,
So is
right?
that technically just like 12 3/4 then? Or is
Yeah,
it
so let's-
something outside of
Let's go there. So this would be 6 plus, now the 6 and the 2,
which is
like this 6 and this 2, they don't have an n directly attached to them, so the sigma is not going to affect those at all. So I would do exactly what you said and say 6 plus 12, sigma
Me too.
from 1 to infinity of 3/4 to the n. And now this is in a much easier form for us to be able to actually evaluate this and get some kind of an answer. So this would be where we'd go 6 plus 12 times, it would be a. Now for me, what's my a? 3/4, yep, over 1 minus r. And of course my common ratio is 3/4. So this would be 6 plus 12 times 3/4 over 1/4. And 3/4 over 1/4 is 3, times 12 is 36, plus 6, there's your 42. So 42 feet. Yeah, we got that in there. Okay. So what do y'all think?
I mean, it's crazy.
Math is crazy. Yeah. But it should, the lovely thing about math, you can say math is hard or crazy or whatever, but in the end, shouldn't math eventually make sense? It should. Now, you can argue all you want that, man, sometimes it's really difficult and sometimes I feel like I never get it, but it should make sense.
That's what a math teacher would say.
It should make sense. I'm not saying that, like, if it doesn't make sense, there's something wrong with you. I'm not saying that at all because we all get confused sometimes, right? I'm just saying it should make sense, which is a lovely thing about math. Yeah.
Why doesn't it equal the same thing if you use 12 as your a value?
You can.
I think you just have to get a phase shift and consider if you added too many numbers in there. So let's see here. If you did it that way,
If you did it by 12, if 12 was your initial, then that would mean that 6 was your initial, then you'd have to subtract 6 instead of adding 6.
so if you got 48, obviously you added like an imaginary up
Like
bounce.
Like it shot up first.
Right.
Yeah.
That's what it would be.
Does that make sense? Did you get 48?
Well, that's what I'm trying to get at here. I'm trying to just
Yeah.
because it seems
So let's think this over. So if you did, so if you did this, think about it like this. If you did 12 times 3/4 to the n, and you said that would be from 0 to infinity,
right.
and then maybe times 2 in there as well. Oh no, well that'd still be 6 times 2.
Yeah.
I would leave the 2 wouldn't need to be there in that case. Yeah, so I bet you if you did this, you'd get 48, right?
Yes.
Yeah.
Yeah. And so if you did that, do you see how this is going to be kind of difficult?
And then you subtract that extra 6 bounce that you have in there.
Yeah, because there really isn't. So like you're putting in this imaginary red bounce that never happened if you do it that way.
Yeah.
So we just have to take that out, like you said, by subtracting 6.
So, what I'm just trying to like think about a way that because a lot of this was taken from like
No.
when you chose to add the 6 instead of including the 6 in your notation like really early in the problem.
Yeah.
And then after that you took the 12 out and that
So
that was
this
something that you did like kind of like based on a lot of experience. I'm trying to kind of get to that place.
so this 12, let's talk about this. So I think there's 2 different things going on here. This 12 that I'm highlighting right now, I took that out as more of a procedural thing.
Mm-hmm.
Because my thought was it's 12 times the summation element. Let me get that out of there to make my summation evaluation easier. So this, I would say this is not based on any kind of experience. It's based on more just a property of summation and my idea of I don't want that 12 in there when I'm trying to do my a over 1 minus r. Now, I agree that this 6 is a whole different thing, right?
Yeah.
And I don't know if I would even say experience so much as I approached it not, this is going to sound so weird, I approached it not mathematically. I didn't look at it and say, what math formula can I use? I approached it from, what's happening?
Okay.
And my first thought was, I drew the picture, my first thought, and like literally when I've done this question before, and when I did it just now, my thought isn't, how can I apply a math formula to this? It's more about, let me think about what's really happening. Okay, it dropped 6, and then the pattern started. So my thought was, I'm just going to start off with this sort of like lone wolf thing, this 6, and think, okay, now that this pattern has started, now I can start to apply some kind of mathematical formula, principle to it that'll allow me to get where I need to go. Does that make sense?
Okay, yeah.
So it wasn't like necessarily an experience-based trick. It was the physics teacher in me saying, what's happening?
Mm-hmm.
And how can I express what's happening?
Okay. Because I just kind of wanted to get to a place where, because I wanted to just use the mathematical formula and just think about things from the mathematical side.
Yeah.
But it seemed like there was some like reasoning and stuff that was kind of going beyond that, and that kind of screwed me up because
Sure.
just because.
Sure. Okay. I'm going to do something on the whiteboard real quick. So let's see here. This might feel a little bit like, and let's see here. Justin's not here. It's not going to come through. This is not going to go through on the video very well. And I don't, you know what? Maybe I'll try this. I might have room. Give me 1 second. So I would just like for him to be able to see it too. So I'm just going to do it here. 'Cause I think there's. I don't think a picture does this justice at all. I think you kind of need to hear it and see it being developed instead of just like a picture. So I want you guys to think about this. If just going to draw a little picture here. If I drew this lovely graph, and I'll just draw it something like this. If you're a lovely graph like that, we're going to call this f of x. And if I did the integral, and I'll put a 1 right here. I did the integral from 1 to infinity of f of x dx. Would you agree with me that that's something that you have actually done before?
Sure thing.
Right? It's a improper integral. We had to use a limit to be able to do this, right? Improper integral. So we recognized that right endpoint wasn't really an endpoint. It was unbounded behavior, and we used the limit, and we found our antiderivative. We applied the limit. We got some number, or we got diverging, right? Infinity. And so all those skills are going to potentially come into play here. But what I want to point out is this. If I told you that this equaled some number, and I don't know what number, I'll just make something up. I'll say 2. Say that it converged to 2. If we were to say that there was a series, and the series was based on f of n, right? So it was the same sort of function generating these terms in the series. What's different here is that, let me draw this like so. This lovely red function is nice and continuous, right? We plug in any x value and get out a y value. But if I think of this like a series, don't we plug in all whole numbers? Like plug in a 1, plug in a 2, plug in a 3, plug in a 4, so on and so forth. I don't plug in every single number in between the 1, 2, 3, 4, 5. I just plug in the 1, 2, 3, 4, 5, right? So then wouldn't the series potentially look like this? Right, the series, I missed on that one. The series would not contain every single fractional and decimal number in between. It would contain only the integer values, right? So if I said this, if I told you that if I said something along the lines of, if the integral converges, the series converges, could you buy that?
Yes.
If the integral converges, the series converges. Just ponder that for a second. Why would that be true?
Because you're actually, well, it depends on if you're doing a right sum or a left sum.
Just based on the way that I drew it. Just stay with how I drew it for a second.
How you drew it, yes.
Why would, again, I'll say the statement, if the integral converges, the series converges.
Well, yeah.
And focused on only my drawing for now. We'll talk about your idea in a second. Why would that be true? What are you seeing?
Because if the graph converges to one of the axes, then the area underneath the curve would converge to one of the axes as well,
Why? Because the rectangles are...
approaching to zero.
How do the rectangles relate to the red graph?
They're below the line.
Aren't they always below?
Yeah.
Right? And I think that's kind of what you're getting at. So if the red graph causes a converging value, I guess I should, converging to a real value, then wouldn't numbers that are always less than that also converge? Okay.
Eventually, wouldn't, or the left sum, wouldn't the left sum approach the two? Because this would approach, with this graph at least, would approach a straight line, and so it kind of wouldn't matter one way or another if you went left or right sum.
Well, we're going to get there. We're going there. In fact, maybe we should go there right now. So then the other way to look at this, of course, is how what Jack just mentioned. I'll use green for this. If I used a left sum, wouldn't all of these rectangles look like that? They'd all be slightly above. So this is where it gets a little bit harder to think about. If you said, if the red graph converges, and we looked at it, instead of n equals 1, we started n equals 0 or something like that. Or the way that I drew it here, didn't I start off at 2 versus 1? So what if I started off at 1 this time instead of 2? If the red graph converges, would the green series still guaranteed converge?
Yes.
Yes, it would. It would. Let me ask you this. This is a very informal treatment of this. I like the visual nature of this. How is the green series different from the blue series?
It's just got a little bit extra.
That's
the green, the first green rectangle.
Yep.
That's the only extra that's there.
It's exactly right. So let me point to it like this. Isn't
average of the two.
Now listen, isn't this blue rectangle the exact same as this green rectangle? They're exactly the same, aren't they? And then
I was going with that.
isn't this blue rectangle exactly the same as that green rectangle?
Wait, that's cool.
So aren't we just like out of phase by one rectangle?
Yeah.
And where's the extra one? It's right there. And we know that green rectangle by itself is finite, right? I mean, it's got a very defined area. So if I take that one extra rectangle and I add it to something that I know converges, the whole thing would have to converge, right? So if I told you, think about it like this. If I said, hey, this integral converges to 2, and you're like, okay, cool. And I'd be like, but what happens if you added 5 to the end result?
Well, it just converges to 7.
It would be 7 now. That makes sense? It wouldn't be like, oh no, you added 5, all of a sudden it diverges. That doesn't make much sense, does it? Okay, so I want to erase all these, and I'm going to change a couple things about what I've got up there. And let's see here. I'm going to erase a bunch of stuff. So be patient with me here. If if you wanted to go back and watch the video and see all this developed again, oh, my 1, 2, 3, 4, 5 went away. That's all right. I'll survive.
So here's a question.
Hang on once. I'm so sorry.
No
Logan, give me 1 second. Let me.
Silence.
I'm not against questions. I just want to do one other thing. So please don't forget your question. So hopefully, just visually at least, I showed you that if the integral converges, then the series will converge. Now there's another side to this, and it's here. Okay, so before I get going too far, Logan, what was your question?
So it looked like when you overlap the right and left sums, it looked like the one rectangle was about as much too much as the other one was not enough. Like they were about almost the same. Could you do the average of the two sums?
Well, so it's a curve, so no, that wouldn't get you the exact.
Oh,
If it was a line, then absolutely that would work,
okay.
because it would be like triangle, triangle.
Right.
But it's a curvy-ish sort of a triangle thing, and then a slightly less curvy-ish triangle thing.
Okay,
So it wouldn't
like
be exactly the
average of
same.
each,
It'd
like,
get you closer, but it wouldn't be exactly the same. Wouldn't be exactly the same. Okay, so what if I told you then that integral diverged this time? Like you did the limit and you did all the procedure you learned back in our November or whenever that was, and you found out that this integral diverges, but then we looked at it from a series perspective, right? We generated the series terms. Would it make sense if I drew in my rectangles like this? I'm going to start off with a left sum this time. If I told you if the integral diverges, the series f of n diverges. Let's think this over. So if the red graph causes a diverging integral, can you see how the blue approximation would also have to diverge?
Yeah,
Why?
because that's how.
Because it's, first of all, it's an overestimate.
It's an overestimate. Yeah, it's exactly. I mean, that's the short answer right there, isn't it? If the red integral gets too big and it diverges, then wouldn't something that's a little bit bigger than that have to also diverge?
Something that's a finite amount less, but also still have to diverge.
So it's the same reasoning. That's right. So if I then used a right sum instead of a left sum, it would be the same kind of reasoning. And again, we're doing this very visually here. You can do this pretty rigorously, symbolically too. Can you all see how the rectangles, like before, line up pretty nicely? How this blue rectangle and this green rectangle are exactly the same. And then you just go on down the line, right? So this blue rectangle, that green rectangle, again, exactly the same. So if the blue rectangles diverged, then, well, gosh, the green rectangles kind of would have to also, because they're exactly the same, just like one large blue rectangle less. So this is kind of like spitting in the wind. It's like saying, okay, if I've got infinity and I subtract 9, what do I have?
Infinity minus 9.
Yeah, which is something increasing without bound, right? Does it make sense? So basically it comes down to that first term either being there or not, and that just won't matter in the grand scheme of will this integral convert or will this series converge or diverge.
Oh my god, that's literally, that's so perfect.
It is. It's a great-
What was so perfect? Say it. What?
It's like being,
It's like peeing in the ocean.
Yeah.
Or drinking the ocean.
Or spitting in the ocean or dumping your Pepsi in the ocean or what?
Yeah.
I mean, do you think the water levels are going to go, woo?
It's like drinking the ocean.
That's right. Some people do that, right? They go try to surf or bodyboard or swim or something, and they feel like they swallowed the whole ocean, but the water level didn't drop at all.
I mean, it
Right?
dropped, but like,
The difference
Immeasurable
is
amount,
so
right?
marginal.
It might even
The
be
finest
smaller.
measuring instruments on Earth couldn't measure it, right? That'd be pretty fascinating to know if there was a sensitive instrument sensitive enough to measure that.
Maybe it
Yeah.
won't
Right?
drop because if you don't take off like a whole
I don't
layer
see
of
how that could be
molecules
possible.
from the
The
ocean,
ocean
it
is
won't
huge.
drop because
It's
it'd
like
be.
trying
Yeah.
to empty
How
the
many
ocean.
acre molecules
One
could you drink?
hole out of the ocean, you really think you'd be able to measure how much the entire height of the ocean changed?
and it would
Logan?
take extra
You're
time
hurting.
because you can't take the
You're
you
hurting
can't
my
empty
brain.
the sand
You'll build
or the spoon into the sand because the sand just pours through the water will eventually make its way back into the ocean. So you're not gonna.
Okay.
So you gotta empty it into the grass
And empty it.
a mile away.
These are all like really lovely illustrations. Let's use this now. So last time you guys learned about the mean coach, the really tough coach. Who was the really tough coach?
Oh,
The one that would only tell you if you messed up. Nth term test for divergence, right? So the nth term test for divergence would tell you, well, it would tell the series, hey, you diverge, but if the series is heading for convergence, it's silent. Doesn't say anything. Then you learned about a little more of a fair coach. This fair coach would tell you whether you converge or diverge. And not only that, but you could eventually find out exactly what you converged to, potentially. What was this really fair coach called?
The geometric.
Geometric series test, the GST. So this particular test is also, the problem with the geometric series test, though, is it was very focused, right? It could only really speak to geometric series. And so, good coach, but very limited in scope. The integral test, and this thing later on we'll call the P-series or the P-series test, or affectionately known as the P-test. Nice foreshadowing with that.
You're welcome, guys.
We'll find that these are also very fair, some, fairly limited still, but very fair in that they'll tell you either way what's happening. So the integral test is right here. So the integral test has a condition, or you could even say 3 conditions, and it's this. The graph of f has to be positive, continuous, and decreasing. And this has to do with those rectangles we just talked about. If f is not always the same sign, like always positive, then you're going to get some positives and negatives. You're going to get kind of an adding out effect, which we will look at soon, but it wouldn't apply for the integral test. Continuous and decreasing. Remember how we did the right sum and left sum idea in my little proof there? If the graph is not continuously decreasing, if there are some parts where it was increasing as well, wouldn't the right sum, left sum properties get switcherooed?
Yep.
So what you would really need to do is identify the portion of the graph where the graph begins to monotonically decrease or strictly decrease. So those are your 3 conditions, right? Positive, continuous, decreasing. Okay, so if those 3 conditions are in place, then if the integral converges, the series converges, or if the integral diverges, the series diverges. And I hope that you're listening right now, because what I'm about to say is a common screw-up. So the series and the integral will both converge or both diverge. I put in here not necessarily to the same value. I'm just going to put pretty much never to the same value. So if the integral converges to 5, it's very likely that the series would not add up to 5. It would add up to something other than 5, but because the integral converged, the series would converge. We just wouldn't exactly know what it converged to. And here's the reason why. Doesn't the integral add up all the little fractions and decimals in between?
Yeah.
Whereas the series adds up just the integral or the integer values along the way. So you're getting all these different decimals and fractions in between, which the series would not be adding in there.
Is there any function?
He was talking about.
I don't think so.
The greatest integer function.
It's got to be continuous for this to work, though, and that's not continuous.
Jack.
So I think trying to find exceptions or find like the one thing would be interesting. We just don't have time to sit and explore. It would be fun. I agree. Yeah.
So I'm still confused on why it has to be decreasing.
So you remember how I talked about underneath, like left sum, right sum, below, above, and how we talked about, well, if this is going here and I've got right sums and left sums, you would get extra rectangles that you wouldn't be able to account for, right? So and we can find series that do this where, here'd be a graph of the function generating the series, right?
Yeah.
So remember how we had like that first rectangle was the one that was like extra? Well, then if we're doing a left sum, we'd have these others that are below, right?
Yeah.
And the whole above and below thing would get completely backwards for that little portion. So it's not that hard to deal with, though. Like if we did have a part where the graph was increasing, you know what we would do? We would just start our n value here and find the convergence or divergence of that.
Oh my god.
Right?
Because we're adding because we're just.
And this would just be adding a finite sum onto it, right? So if I found out that we would get convergence here, wouldn't it just be convergence plus some number? So the answer is it converges. If I analyzed the blue part and I found out that the blue part diverges, well, I'd say, well, I get a diverging sum plus 10. What's the answer? Diverges.
So it could literally, if it converges on any interval from C to infinity,
Yes.
any values.
Any interval from C to infinity, then you know whatever was before that,
Ugh,
you know,
that's
from
so
1 to
cool.
C, let's say, was a finite amount. You just add that finite amount to the converging part and you get converging.
What if it's like,
I don't know, I'm guessing.
Does that mean?
I got lost there. Was there a vertical asymptote in there?
yeah, what if it has a vertical?
It's got to be continuous. So the vertical asymptote would screw everything up. So what we would do there is we locate that vertical asymptote and we'd say, well, it's like if you did have a vertical asymptote, you know, like this and this, let's say, we'd only be focused on that part. We'd
Okay.
ignore everything prior to that.
So you wouldn't be able to do it for the entire function because it's not.
No, and this is where like a series, of course, could be connected to the function, right? But you could only use part of the function to generate the series if you got some vertical asymptote. Does that make sense?
I mean, yeah, it makes sense, but I'm just thinking about like,
You're trying to too closely connect the function with the series.
oh, because series can only be whole numbers.
Yes,
Like, we
exactly.
skip over the asterisk.
No.
Well, not necessarily we would skip over it. We just wouldn't start it with the,
Like,
we just wouldn't start the series in such a way that the asymptote would be within the domain of the
like
series.
you just wouldn't, yeah.
Yeah.
Wouldn't be a part of your life.
It wouldn't be something that we would seek out. We wouldn't seek that. It would be something that would just sort of have to happen. I don't know how it would just naturally happen, but we wouldn't say, hey, let's throw an asymptote in there and just see what goes on.
Yeah.
I don't think we'd do that just for, I don't know. Again, if our class was like, if our class met for like 4 hours a day, every single day, maybe we'd have a chance to do something like that. I think it would be fun, to be honest with you. Okay. So in a minute, hey guys, listen up, please. Hey, in a minute, we'll do one of those. In fact, I tell you what, I think I'm going to do one of them now. Yes, I'm going to do one of these right now. So take a look at number 1, and I'll come back around to the P series and the harmonic series, that whole thing. So guys, check this out with me. Guys, this is probably going to be our one and only example, so please be checked in. So if you looked at number 1, and let's do a mental nth term test. So if I did the limit as n goes towards infinity of that nth term, what would I get?
0.
Right? Isn't the degree of the top less than the degree of the bottom? So in my head, I do this quick nth term test, and I say, all right, nth term test tells me 0, also known as,
We don't know.
it's not telling us anything. We don't know anything yet. So I would say, all right, I would like to use, guys, all these decisions are super crucial, right? So you can know when to do what. Maybe then you think, all right, the nth term test didn't tell me anything. Why don't I use the geometric series test? Why can't I do that?
It's not geometric.
How do we know it's not geometric?
Because it's not like a.
It's not.
I can't tell you the exact
It's
answer.
not.
It's not a number to the n,
Yeah.
like 3 to the n or 3/4 to the n.
You know what I meant.
To be geometric, it's got to be a numerical value to a variable exponent, and that's not, in fact, isn't it the exact opposite?
Yeah.
It's a variable base with a numerical exponent. It's completely the opposite. So, one of the things you might consider doing, this is not the only thing you could do here. At this point, you might say, let's do the integral. No, the p-test doesn't fit here either. You might say, let's do the integral test. So the conditions for the integral test is the graph has to be positive, continuous, and decreasing. And can I throw, listen please, I got to throw one more condition in there, and it's like sort of common sense. don't you have to be able to find the antiderivative of that?
I mean,
So if you want to do an antiderivative, you're like, cool, let's do the integral test. It can be awesome.
Oh,
And then you look at it and you say, well, I don't even know what the antiderivative is. You probably shouldn't use the integral test. But here, you saw it, didn't you? It's going to be ln. So here's what I would do. I would confirm, and I would say n over n squared minus 1, or n squared plus 1, excuse me, is positive. How do I know that it's positive? What am I thinking there?
You're starting at n equals 1 and it'll just increase.
That's right. And 1 squared is positive, plus 1 is still positive, and if the numerator is 1,
And there's always
it's a positive over a positive. And then, like Logan said, the numbers are just going to go up from there, are they not? So every
Therefore-
single term will be positive.
We've made it positive.
Continuous. How do I know that this graph would be continuous?
there are no asymptotes.
There are no vertical asymptotes because the denominator
Never equals 0.
could never be 0, not with real numbers at least, right?
I.
Okay, so positive, continuous, and the last one is a little bit tougher to do without a graph. And this is where, listen, this is where in a situation like this, I'm not going to play gotcha. There's this one little part where it's like, and then goes down. It's not going to be that way. Consider what's happening here. If you start plugging in a 1, 2, 3, 4, 5, isn't the denominator getting squared plus 1? It's going to be a fraction getting smaller and smaller and smaller. So I'm not going to ask you to prove this. I would just want you to recognize that that's what is happening and say it. That's all you got to do. Okay, so those are your 3 conditions there. And then I'm going to do, Peyton, go ahead.
Would there ever be a situation on a test or a quiz where we would have to take the derivative to see where it's decreasing and then do it?
I'm not going to say, yeah, and that would be a way to prove it, right? You could say, hey, its derivative is always negative.
Like, would we have to find where the derivative is negative? And then
So
use that?
I think that that's a valid thing that somebody might have to do. I think it's probably a bit over-involved for a quiz or a test. I haven't seen... So this is where I want to be careful and say there's no way you would ever see this on the AP test. You could, but it would just be like a tiny part. Like they would say, hey, the integral test can work. Which of the following reasons would be proof for that?
So
And one of them would be f prime of n is negative for this interval, right? So
it wouldn't be like, you wouldn't have to find the derivative.
yeah, I don't, like, if it was a bigger question like this, I don't think that would be a part of it. I think it would be easy enough to where you'd be able to say, oh, look, the terms go consistently. So, but I wouldn't be against them or me doing an example like what I said, Like, which of the following would prove that the integral test actually works? And that being one of them, yeah.
Why are you doing it in a row?
Because I'm going to do the integral test.
Because the integral, if it diverges, the series diverges.
And if the integral converges, the series... I just need to find out if this integral converges or diverges.
But you don't need to know but if they're not like the same. Or you don't even know the actual number.
At no point does it say, and what is the sum? It just says, does this series converge or diverge?
So that's why you can do the integral, it doesn't matter.
Right. So our answer is binary. You're going to say converge or diverge almost all the time with these. And rarely, in only one case, will it say, and it converges to this number. In what case? Geometric. And since this isn't geometric, we're not going to go there. Okay, so let's see here. Next step
Gives me so much life.
would be limit as b goes towards infinity, and it would be 1/2 natural log of n squared plus 1, evaluated from 1 to b,
Yeah.
right?
It's always positive to take away the absolute value.
That's true. That's very
Useless,
true.
but true.
Thank you.
I don't know if I'd say useless or not, but it's good. Okay, so then you get ln of 2 for this other one, right, when you plug in the 1. So this is where you get to finish this off. Obviously, the second term, the limit doesn't even apply. But the first term, b gets really, really big, and it gets squared, and then you add 1. What is ln of that doing?
That's big.
It's just making it a little bit smaller.
No, getting bigger and bigger and bigger, isn't it? Well, it's saying it's making the output a little smaller?
Yeah.
Sure, exactly. But still heading towards infinity, correct? Yeah.
Yes.
So infinity minus 1/2 natural log of 2, still infinity, right? It's that 1/2 ln of 2 thinks it can handle the infinity, but it can't. Okay, so then what we can say is, because the integral diverged, the series does too.
This guy, not this guy. It's like a really dark.
Why'd you say the series? Or the-
Yeah, you can just say the series. You can say the series if you want. And of course, the reasoning that we are using there is called the integral test. I don't think IT is a good.
P series on Wednesday.
Well, I'd like to talk about it right now if I can, but not a full treatment of it, but I'd like to mention it briefly. Santi, your question?
I was just gonna say if I actually wrote like integral and series instead of rewriting
Oh, if you said because the integral diverges.
like the actual word integral.
Right, yeah. You literally go, quote, because the integral diverges, the series diverges.
Yeah.
I'm good with that.
Okay, cool. Can I say the sum diverges? Or I guess it would just be series.
Yeah, well, series is a sum.
Okay, so if I said sum, you'd be alright.
Series is probably best because that's more to the point. But
Okay,
yeah.
that's fine.
Okay, so I think you guys will find honestly, the p-test is very, very focused, but if you can identify a p-series, it's super duper easy. And the harmonic series test is also very recognizable. Maybe you're starting to get the idea that if you can recognize what type of series something is, it makes things so much easier. And that's why I spend the time saying, would I use this? I don't know. Would I use that? Well, if this didn't work, what would I use? We'll do a lot of that in the coming days and weeks. So, let's see here. We, this week, have a quiz. It's the polar quiz, and I want to say it's on Thursday
It's on,
or Friday?
it's on Wednesday.
It's on Wednesday?
It's on a day that I
Okay,
can
so-
do it on Thursday?
Yeah,
What?
please.
Can we take it on Thursday? Is it a possibility?
That would be nice.
Just switch Wednesday and Thursday.
Why?
We have physics.
I have a
test.
physics.
Well,
Yeah.
that's true. We have a lot of stuff going on.
Yeah,
I'm
not
you
gonna
think
be
going
here,
on?
I have no reference.
I guess I will consider, but I'll look at my calendar to see if it makes sense or not.
Can you let us know soon?
I'll look at it right now. I'll look at it this afternoon.
It's like, I'll let you guys know Wednesday.
I will be taking it tomorrow, so.
So then when I see you next, when we have a regular class next, we will cover the P series and the harmonic series test as well. So
Thank you.
yeah, the only issue I would have, listen, the only issue I would have, guys, you should all hear this. The only issue that I would have with you guys doing the polar quiz later is that we have that parametric vector polar test coming up next week. You will have less feedback time on the back end. Does it make sense? You would still get some feedback time, but you would have less of it.
Mr. Anderson, can I make that on Monday, Tuesday or Wednesday?